Section 11.3 is on page 759, talks about the Eragon test and estimates of sum. So those are two different topics. We're going to get the Eragon test out of the way. The Eragon test states, well, suppose that a function is continuous, positive, and decreasing on an interval. I'm going to alter that. Instead of 1, I'm going to make it from a to infinity. And let a sub n equal some function of n. Then the series from n equal 1 to infinity is convergent if and only if the integral from a to infinity is convergent. Right? You could alter that to a, or you could leave it. I'll talk about that when we get there. If the integral from a to infinity of f of x dx converge, then this sequence converge. And if the integral from a to infinity diverge, then this series diverge. So this is running from 1. If I'm running from 1, and instead of running from 1, a is 5. If I could show that the series from 5 to infinity converge, then adding 5 more terms to it will not make a difference. And if I could show that the series from 5 to infinity diverge, adding 5 more terms to it will not make a difference. So 3 things you have to really state. Continuity, you have to make sure it's positive, and you have to show it's decreasing, unless n only appears in the denominator. You know, there are exceptions, slight exceptions, but those are the bare minimum we will take. So use the integral test to determine whether the series convergent or divergent. This is on page 765, and this is pretty much going back to indefinite integrals. If you remember, we did those back in the days. Indeterminate, I think, integrals. Section 6.8, I think. No, I'm sorry, 7.8. Improper integrals. So, I'm glancing at this problem. If I look at this, that's really the series. That's really the series n equal 1 to infinity of 1 over n to the 0.3. Well, positive, that's fine. You could just say positive. It better be, you don't have to show work. Continuous, you know where those are continuous and not continuous. You know, since n is always 1 or bigger, that's not continuous at 0. No problem there. Now, this is the deal. If you want to say decreasing, if n only appears in the denominator, I'll accept that. Otherwise, you have to show that a function is decreasing. And if you remember how we show a function is decreasing, you take a derivative and show its derivative is negative. So, then I could say, well, it's positive, continuous, and decreasing. I'm going to look at the integral from 1 to infinity of 1 over x to the 0.3 dx. Well, that's really x to the negative 0.3, so that's going to be x to the 0.7 divided by 0.7 evaluated from 1 to t, taking the limit as t approaches infinity. And that would be the limit as t approaches infinity of, this is really t to the 0.7 over 0.7 minus 1 over 0.7. In case you're wondering, t to the 0.7 is actually the 10th root of t to the 7. And as t approaches infinity, this will approach infinity. Therefore, diverge by the integral test. And that's how it works. Next problem up, we're looking at number 6. Well, same deal. We look at this, we say, well, this is positive. Okay, it's always positive, that's true. It is continuous. Well, this is only not continuous when n equal 1/3. Since you start at 1, beyond that, you're okay. Decreasing is allowed to say for this problem because n only appears in the denominator. And now you're pretty much integrating from 1 to infinity, 1 over 3x minus 1 to the 4th dx. Then here you would let u equal 3x minus 1. du is 3 dx. So this is 1/3 the integral of u to the 4th du. That's really u to the negative 4. So add 1 to the power, divide by that. That'll be the integral of, that'll be u to the negative 3 over 3, right? And that would be negative 1/9 of 1 over u cubed. And if I substitute back in, I'm looking at the limit as t approaches infinity of negative 1/9 of 1 over u was 3x minus 1 cubed minus 1 over 3x minus 1. I'm sorry. I'm rushing ahead. Evaluated from 1 to t. That would be the limit as t approaches infinity of negative 1 over 9 times 1 over 3t minus 1 cubed minus 1 over, we put a 2 in the 1, 3, that's 2 cubed. You know what, I am going to fit this underneath. That fits. Okay. And then I'm going to say that's going to be a 0, so that's going to be, let me see, negative times a negative, positive 1 over 72. Therefore, converge by the integral test. Okay, I moved that a bit to make it look better, I guess. We'll see. If I could find more space, I'll rearrange. Now, let's get this out of the way. In general, if I'm looking at the series n equal 1 to infinity of 1 over n to the p. In general, well, this is positive. That's very good. Continuous, that's very good. If you want to say decreasing, you gotta be careful. This is decreasing only if p is bigger than 0. Even if it equals to 0, it's a problem. If it equals to 0, that's 1. That's not decreasing anymore. Right? So p must be bigger than 0 for this to really be decreasing. And if I look at the integral from 1 to infinity of n to the negative p of x to the negative p dx, that is, add 1 to the power, divide by that, evaluate it from 1 to t, taking the limit as t approaches infinity. Oh yeah, that's infinity right there. And that is the limit as t approaches infinity. 1 over 1 minus p is a constant. I'll talk about that in a minute. And this is going to be t raised to the 1 minus p minus 1. Now think about it. I want this to converge. Well, if this power is negative, if 1 minus p is less than 0, then the limit as t approaches infinity of t to the negative to the 1 minus p will be 0. That'll 0 out, and therefore it'll converge. If 1 minus p is positive, if this happened to be a positive power, then the limit as t approaches infinity of t to the 1 minus p would be infinity, and therefore it'll diverge. And of course, if p equal 1, I'll get to that in a minute. I'll show you what that means. It turns out to be included right there. So, anywhere I'm looking at a power series that looks like 1 over n raised to a power, even here I could have thought of that as n being raised to the 4th. If p is, and now if I solve, doesn't that mean here p is greater than 1, and here p is less than or equal to 1? And that's called a p-series. Think about it, what it means if I'm looking at, and I could do this really quick, I don't need that much space. If I'm looking at the series of 1 over n in which p equal 1, isn't that positive, continuous, decreasing? And isn't the integral of 1 over x dx natural log of x? and if I take the limit as n approaches infinity, right, of natural log, if I take the limit as t approaches infinity of natural log of t minus natural log of 1, isn't that infinity? So instead of saying harmonic, you could say p-series now. And this is really how we're going to conclude the next test, which we're going to use for a lot of our applications. So my conclusion is that this is the p-series test. If you use the letter p, I'm going to assume you're referring to the p-series. If you're not referring to the p-series, do not use the letter p. And if you use G and R, I'm assuming you're talking about geometric, and R is the common ratio. If you mean anything other than geometric and the common ratio for G and R, do not use those. Use something else. So, now that I looked at this, instead of doing all of this work, here it says use the integral test. But on the exam, I'm not going to specify. You could use whatever test you want. If I gave you number 4, you could look at number 4 right now and say, well, wait a minute. P is 0.03. That's less than 1. Therefore, it diverges. No need to do any of that work. Actually, I have to force you to use the integral test, and I don't. I have to go out of my way. If I throw a log in there, it becomes tedious, but then I'm going to show you a shortcut even around that. So, let's look at the next problem. Problem number 8. I want to figure out whether this series converge or diverge. Well, let's see. This is positive, I agree. Continuous, I agree, because exponential can never be 0. Decreasing, not so fast. You have to show me that this is decreasing. So, before you jump and start from the integral and on, you're going to go on this side and you say, well, let's see. F prime of x is going to be, I could use the product rule, I could use the quotient rule. This is really the series n equal 1 to infinity of n squared over e to the n cubed. So, I could take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And that would be if I factor an x e to the x cubed out. So torn here. That would be a 2 minus 3x cubed squared, yeah, over e to the x cubed squared. Well, that cancels one of those, not a problem. So I'm really testing x equals 0. And if I take 2 minus 3x cubed, set it equal to 0, that would mean that x equal the cube root of 2/3. Is that right? And when I get to the testing, when I get to actually, I want to test this, well, you know what? There is 0, and there is this cube root of 2/3. I shouldn't worry about negative. Remember, x represents n. I shouldn't even worry about that. I should worry about to the right. Do you see that this is 2/3, this is less than 1? So maybe from 1 and on. If this was 3.2, I would have started with 4, you know? Just saying. So, if I pick a point to the right of 1, say 2. Well, that's positive. 2, that's 8 times negative 24. 2 minus 24 is negative. If the derivative is negative, the function is decreasing. Now you could say, after you show this, you could say decreasing. That's fine. And now you're going to do the integral from 1 to infinity of x squared over e to the x cubed dx. You're going to let u equal x cubed. Du will be 3x squared dx. So that's 1/3 times the integral of e to the negative u du. That is 1/3 times e to the negative x cubed evaluated from 1 to t, taking the limit as t approaches infinity. And that would be the limit as t approaches infinity of 1 over 3 times 1 over e to the t cubed minus 1 over e to the negative 1. Well, we know this is going to approach 0, so that's going to equal negative 1 over 3 e to the negative 1, therefore converge by the Eragon test.